4 billion years ago, Mars was wet, not damp, not occasionally moist, genuinely, substantially, persistently wet. The evidence is written across the planet's surface in a language that took us decades to learn to read. Ancient river valleys stretching hundreds of kilometers, lake beds with the chemical signatures of prolonged standing water, minerals that only form in the presence of liquid water for extended periods. A northern hemisphere that may have held an ocean covering a third of the planet's surface. Kilometers deep in places, lapping against shorelines that are now frozen desert at altitudes that make no geological sense unless you accept what they imply. Mars had water. Mars had a hydrological cycle. Mars had weather in the way that Earth has weather. And Mars, at some point in its history, lost almost all of it. We thought we understood how Mars lost its water. The story we told ourselves was tidy and well supported and consistent with decades of observation. Large global dust storms, the kind that periodically engulf the entire planet in a curtain of red that Hubble can photograph from Earth, were the primary driver. When these planet-wide storms raged, they lofted water vapor high into the atmosphere, where solar radiation broke the molecules apart. Hydrogen escaped into space, and Mars became slightly drier. Over billions of years, through thousands of these global events, Mars lost its water gradually to the relentless process of atmospheric escape. That story is not wrong exactly, but research published in early 2026 has revealed that it is dramatically incomplete. The mechanism we missed is not exotic or theoretical. The data revealing it was sitting in the archives of 3 separate Mars-orbiting spacecraft. And the storms responsible for it are the small ones, the regional events we barely bothered to study because we assumed they were too minor to matter. We were wrong, and the implications of being wrong change everything we thought we knew about how Mars died. To understand what the new research found, you first need to understand the physics of how a planet loses its water to space. Water is H2O, 2 hydrogen atoms bonded to 1 oxygen atom. On Earth, the vast majority of water stays on the surface or in the lower atmosphere, held there by gravity and by the chemistry of our thick, protective atmospheric blanket. The water cycle moves water between ocean and atmosphere and back again, but very little of it escapes to space. Earth has been losing hydrogen to space at a slow, steady rate for 4.5 billion years, but the rate is low enough and the water supply large enough that it has not meaningfully depleted our oceans. Mars has no such protection. Its atmosphere is thin, roughly 1% of Earth's surface pressure. Its magnetic field is essentially absent, stripped away billions of years ago when the planet's core cooled and its internal dynamo shut down. Without a significant magnetic field, the solar wind, the continuous stream of charged particles flowing outward from the sun, reaches the upper Martian atmosphere directly and drives atmospheric escape processes that Earth's magnetosphere deflects. The specific process that removes water begins with photolysis. When water vapor reaches the upper atmosphere, it encounters ultraviolet radiation from the sun. The UV radiation has enough energy to break the chemical bond between the hydrogen atoms and the oxygen atom, splitting the water molecule apart. The oxygen tends to recombine with other atmospheric molecules or fall back to the surface. The hydrogen, the lightest element in existence, is far more vulnerable to escape. At the exobase, the boundary where the Martian atmosphere transitions into space, hydrogen atoms that have been accelerated by interactions with the solar wind can reach escape velocity and leave the planet permanently. Every hydrogen atom that escapes from Mars represents water that Mars will never get back. The hydrogen is gone. The oxygen eventually combines with surface minerals, contributing to the iron oxide that gives Mars its red color. And the planet becomes slightly drier. 1 molecule of water at a time, Across billions of years, Mars has been bleeding into space. The question has always been, how fast? And the answer determines how much water Mars had to begin with, how quickly the transition from wet world to desert happened, and what the Martian climate looked like during the window when liquid water was stable at the surface. Before 2026, the answer was mainly during global dust storms, mainly during certain seasons, at rates that our climate models could account for. The new research says the answer is more complicated, more violent, and more surprising than any of that. The discovery came from a dust storm that nobody was paying particular attention to. In the Northern Hemisphere summer of Martian year 37, which corresponds to 2022 and 2023 on Earth, a regional dust storm erupted in the northwestern Syrtis Major region of Mars. This is not an unusual occurrence. Mars is a dusty, windy planet. Regional dust storms, events covering areas of roughly 1 million square kilometers or more, but not the entire planet, happen regularly. They are studied. They are cataloged. They are considered moderately interesting, but not transformative events. What made this storm different became apparent only when an international research team led by Adrian Brines from the Instituto de Astrofísica de Andalucía and Shohei Aoki from the University of Tokyo and Tohoku University decided to look carefully at what multiple orbiters had recorded during and after the storm. They were using data from 3 separate spacecraft simultaneously. The ExoMars Trace Gas Orbiter, which carries the most sensitive instruments ever deployed to measure the chemical composition of the Martian atmosphere. NASA's Mars Reconnaissance Orbiter, which has been imaging and profiling the Martian atmosphere since 2006. And the Emirates Mars mission, the HOPE probe, which was designed specifically to study the Martian atmosphere and its relationship to space weather and atmospheric escape. 3 independent instruments on 3 independent spacecraft, each measuring different properties of the Martian atmosphere from different orbital perspectives, all pointing at the same region during and after the same regional storm. What they recorded was not what existing climate models predicted. The dust storm did something that small regional storms were not supposed to be able to do. As the storm intensified, the dust particles absorbed solar radiation and heated the surrounding atmosphere rapidly and dramatically. This rapid, localized heating drove intense convection, the same process that drives thunderstorm updrafts on Earth, but operating at Martian scales and with Martian dust instead of water droplets. The convection columns reached extraordinary heights, punching through the layers of the Martian atmosphere that normally act as barriers to vertical transport. Water vapor was carried upward in these convection columns to altitudes it should not have been able to reach during Northern Hemisphere summer. At those heights, water concentrations reached 10 times higher than typical levels for that season. 10 times. Not a marginal increase, not a statistical fluctuation. A 10-fold spike in atmospheric water at altitudes where solar radiation could reach it directly and efficiently. The photolysis that followed was rapid. The water molecules at those heights were bombarded by ultraviolet radiation and split into their components. The hydrogen drifted upward toward the exobase. And then the HOPE probe's instruments detected what confirmed the entire chain of events. Hydrogen at the exobase spiked to 2.5 times normal levels. The hydrogen that had been water molecules days earlier was now at the boundary between the Martian atmosphere and space, ready to escape to the solar wind. The timing was the second shock. This happened during the Northern Hemisphere summer. That season had been considered, based on decades of observation and climate modeling, to be relatively quiet in terms of atmospheric water escape. The dominant water loss mechanisms were understood to be strongest during Southern Hemisphere summer, when Mars is closer to the Sun and heating is more intense. The Northern Hemisphere summer was a period scientists essentially deprioritized when building models of Martian water loss. The storm happened during that quiet season, and it produced water escape rates that the existing models had not predicted for that season. an out-of-season event in a season thought to be irrelevant, driven by a storm type thought to be too small to matter, producing escape rates that required rethinking how the models were built. The implications extend far beyond a single storm in a single season. Mars's history spans roughly 4 billion years. Over that timescale, regional dust storms are not rare events. They are common, recurring, seasonal phenomena. If each regional storm of sufficient intensity can drive a burst of water escape at 10 times the normal rate, and if these storms occur regularly across Martian history, the cumulative contribution of regional storms to the total water budget of Mars over 4 billion years is not a minor correction to the existing models. It is a potentially significant and previously unaccounted for term in the equation of how Mars lost its water. The existing models of Martian water history were built around global storms and known seasonal patterns. They were calibrated to match the current observed dryness of Mars based on escape rates derived from those mechanisms. If regional storms are a significant additional driver of water escape, the models were underestimating the total escape rate. And if the total escape rate was underestimated, the models may also have been wrong about how much water Mars had to begin with, how quickly the transition from wet to dry occurred, and what the climate was like during the critical window when liquid water existed at the surface. There is also a deeper implication about the nature of climate tipping points on Mars. The current Northern Hemisphere summer is a period of relatively low atmospheric water escape, but the research showed that a single regional storm was sufficient to transform a quiet season into an episode of dramatically elevated water loss. Mars's current climate is not a stable equilibrium from which water loss proceeds at predictable background rates. It is a system that can be thrown into episodic bursts of accelerated loss by weather events that we had considered too small and too local to matter. Over the 4 billion years of Martian history, during which the planet's axial tilt varied significantly, during which the solar output was different, during which the frequency and intensity of dust storms was likely different from today, how many such episodes occurred that we have not accounted for? The answer shapes our understanding of the entire trajectory of Martian climate evolution. Mars was wet for a reason. The water did not disappear overnight. The transition from a planet with rivers and lakes and possibly oceans to the frozen desert we see today took hundreds of millions of years, possibly longer. Understanding that transition at the level of specific mechanisms, specific storm types, specific seasonal patterns, is not just scientific curiosity. It is the foundation of any serious attempt to understand whether Mars was ever habitable, for how long, and under what specific conditions. The question of habitability matters for a reason that has nothing to do with scientific abstraction. The oldest microbial fossils on Earth date to approximately 3.5 billion years ago. The first evidence of liquid water on Mars dates to approximately 4 billion years ago. If Mars had liquid water at the surface for hundreds of millions of years during the same period when life was emerging on Earth, the question of whether Mars was ever inhabited is not a question that can be answered by assuming the planet was always as dead as it appears today. The chemical and thermal conditions in early Martian lakes and rivers were, according to current understanding, broadly similar to the conditions in which early life emerged on Earth. If life did emerge on Mars during that wet period, the transition from wet to dry would have been a mass extinction event of planetary scale. And the mechanism that drove that transition, the progressive loss of water to space through photolysis and hydrogen escape, is the mechanism the new research is helping to characterize with unprecedented precision. The regional storm that nobody was paying particular attention to in 2022 is a data point in that characterization. A small piece of a 4 billion year story, but the kind of piece that changes the shape of the whole story when you slot it into place. There is also a dimension to this research that points forward rather than backward. We are going to Mars. not in the distant speculative future of science fiction, but in the near-term concrete future of engineering programs that are currently building hardware. NASA's Artemis program is returning humans to the moon as the first step of a longer journey. SpaceX's Starship is being developed explicitly with Mars as the destination. Within a generation, if plans proceed, human beings will be living and working on the Martian surface. They will need to understand Martian dust storms with the same precision that weather forecasters need to understand Earth storms. The storms that killed the Opportunity rover, that forced the Curiosity team to manage its power budget carefully during months of reduced solar input, are the same class of events that will determine whether a human settlement on Mars survives or fails. Getting the storm models wrong is not a scientific embarrassment. It is a mission failure mode. The new research reveals that regional dust storms are more dynamically significant, more capable of driving large-scale atmospheric changes, and more effective at redistributing water in the Martian atmosphere than existing models captured. Building those effects into the next generation of Martian climate models will produce better forecasts, better risk assessments, and better mission planning for the human Mars program that is coming, regardless of how much we currently understand. The storm we did not bother to study carefully enough turns out to have been telling us something we needed to know. We were looking at the wrong size of storm. We were looking at the wrong season. The mechanism was in the data from 3 different spacecraft for years before anyone put it together. It was hiding in plain sight. The surface of Mars tells the whole story if you know how to read it. The dried riverbeds that the Curiosity and Perseverance rovers have driven across were carved by flowing water that existed before the mechanism the new research characterizes had fully done its work. The ancient lake sediments that Perseverance has been drilling into are the deposits of a world where water persisted long enough to lay down the chemistry of habitability. The shorelines of the hypothetical Northern Ocean, if they existed, mark the boundary of a world that had more in common with early Earth than with the frozen desert that exists there today. Something destroyed all of that. Something converted a planet that might have harbored life into the most thoroughly studied dead world in the solar system. That something was not a single catastrophic event. It was a process, a long, slow, episodic process of atmospheric escape driven by the absence of a magnetic field, the loss of internal heat, the thinning of the atmosphere, and the relentless work of photolysis and hydrogen escape across billions of years. The answer was in the data from 2022 and 2023. It was in the measurements from 3 orbiters that were already in orbit, already collecting data, already transmitting it back to Earth. The instrument that finally revealed it was not a new telescope or a new rover or a new mission. It was a team of researchers who decided to look carefully at a regional storm that most of the community had filed under routine and moved on. They looked carefully. They connected the water vapor spike to the hydrogen escape spike. They looked at the season and noticed it was wrong, according to the models. They looked at the storm and noticed it was smaller than what the models said should matter. And they found the piece that changes the picture. We finally know what destroyed Mars. It was not one thing. It was not one mechanism. It was not one season or one type of storm or one slow process operating alone. It was all of them together, including the ones we thought were too small to bother with, the ones hiding in plain sight. Good night.